Hello everyone, this is Professor Robert Solis. Welcome to this video lesson. We're going to be talking about this particular circuit and how we would go about minimizing it using DeMorgan's rules. So as you can see over here, I have an exclusive OR gate, and so that would mean A exclusive OR B because A and B are the input signals. Here we have a regular OR gate, so that's going to be B or C. And that feeds into an exclusive NOR gate. So this is an exclusive OR with an inverter at the tip. So what that means is that BC is going to be exclusive ORed with A, and then the whole thing is going to be knotted. Well, if that's the case, that would be BC, and so that's why you see this over here, BC with the OR symbol. That's going to be exclusive ORed with the other input, which is A. The whole thing is going to have a line over it because of that knot at the very end. Finally, we have an AND gate that's going to take this input and AND it with this input. Well, this input over here is A exclusive OR B. The other input is B or C quantity exclusive OR A, and the whole thing is knotted. That's basically this part over here. All right, so this is what the output of the circuit is. And so our job is to see if we can minimize this circuit. Well, at least just for this portion right here, this is the same thing as this. And so basically what I've done is I've taken that exclusive OR away, and I'm going to take that BC and then knot it with A, which you can see over here, and I'm going to AND these two together. And then I am going to OR that with a B or C quantity, that's this over here, and then AND that with A. So basically this gets knotted and then A doesn't, this gets knotted and then B or C does not. And then of course we have this overall line over the top of the entire expression, and so we have to make sure that we knot this entire thing. And just to prove to you that this is in fact the case, if you were to write this over here and write this over here, and then you have three signals A, B, and C, so that means 8 different outputs. If you were to compare the truth table, you would see that both of these expressions are the same. So basically this is confirmation that this really is in fact the, I guess the rewriting, re-expressing this to get rid of the exclusive OR operator. Okay, so then the next thing that we need to do is to use DeMorgan's laws to change and reduce the circuit. So basically we have this right here. So I'm going to take this, I'm going to copy and paste it and move it over here, and then just go step by step to show you how we would go from here. Well, the first thing that I'm going to need to do is to remove that exclusive OR and this exclusive OR. Well, A exclusive OR B is the same thing as A B naught or B naught A. We've already decided what this is going to be. That's this part over here. It's really going to be the same thing as this, so you'll see that I've just rewritten the B or C A naught, the B or C naught A, and then of course the whole thing is knotted. All right, so let's leave this part alone. That's why you see I've just simply rewritten this. And let's do this. So what I'm going to do is I'm going to take these items over here and use DeMorgan's laws. So that over here, this is going to be the A, that's this part over here. This becomes B naught and C naught. So B naught and C naught, that's going to be ANDed with A, and so I have this part over here. Over here with this part, I just simply took the A naught, I moved it in the front, so that's A naught, B or C. So that's just simply moving this to the other side. And of course the whole thing is going to be knotted. All right, for this part over here, we don't touch it, so it stays the same. For over here, for this part, what I'm going to do is I'm going to leave that overall knot. That's all you can see over here that's written, that line over there in the top. And I'm going to AND these two, so that's going to be A naught B. This is going to be A naught C, and of course I ORed those two together. And that is just simply a rewriting A B naught C naught. Okay, so now let's use DeMorgan's rule to break this apart. And so that's going to be A naught B. The naught, we'll change that to an AND operator. This is A naught C with a naught over it. We're going to change this to an AND operator. And then this is A B naught C naught, and we're going to put a naught operator over that. Okay, so what we can do then is we can take this part, again using DeMorgan's rule, so we'll change the AND to an OR. This is going to be A naught naught, and this will be B naught. And so that's this part over here. We'll change that AND to an OR operator, so this is going to be A naught naught, and then the naught of C. And then finally, we'll take these AND operators, we'll turn them into OR operators, and we'll split these up. So that's going to be A naught, B naught naught, you see that over here, C naught naught, you see that over here. All right, so now that we have this, let's rewrite everything so that we can see, for example, the naught naughts are really just simply A. So this is A naught naught is really the same thing as A. B naught naught is really the same thing as B. Same thing with C naught naught, that's the same thing as C. All right, so what I've done is I'll say, let's take care of these two parts over here, and we'll AND them together, and then we'll take these two parts of the equation, and we'll AND these two together. All right, so over here, this A, B naught is going to be ANDed with A, so that's why we end up with this A, B naught. Then we'll have this A, B naught is going to be ANDed with B naught, and so that's where we have A, actually I did this part in first, A naught, B, that's this right here. Then it looks like I did this A, B naught with ANDed with B naught, and so that's this over here. And then we'll do this over here, A naught, B naught, and that's this part over here. So I put a parens over here because this is going to be ANDed with the result of this. This is the result of ANDing these two. Let's see what happens. So that's going to be A naught, here we go, B, here we go, C, A naught, C naught, B, C naught, and then finally C naught. All right, well, anytime that you see something like A naught, that just simply turns into 0. So that's why this is going to be 0, because A and with the naught of itself is always going to be 0. So we strike out all those combinations where there's like B naught over here. That whole thing just turns to 0. A naught, that turns to 0. So let's get rid of those right off the bat. And then the next thing I'm going to do is, if you see something like A B naught, well, the A and the A really just combine into one, because A and A is A. So that's why this turns into A B naught. And this is just simply A, and then B naught is the same thing as B naught, so that becomes A B naught. Let me put a parens around here for that first part, and then let's work on this guy over here. So it looks like I have AB, that's this over here, AC, A naught, C naught, and then finally B C naught. All right, well, A B naught or A B naught is really just the same thing as A B naught. So that's why I just reduced that over here to this one expression, and then I rewrote everything else. And then finally, we're going to AND this with this, and this expression. So if I AND these two, that's going to be A B naught. This is going to be A B naught C. This will be A naught B naught C naught, and then this will be A B naught B C naught. Okay. Well, anytime that I see that B naught or A naught or anything like that, I can just simply cross those out, because those become 0. B naught, A naught, and then over here B naught. So all I'm left with is just this guy over here, A B naught C, but A and A is the same thing as A, so I can just simply turn that into 1A. A B naught C is my ultimate solution. All right, well, that being the case, then if I were to discover what that A B naught C truth table is, let me just go ahead and type in A, B, and C, and type all the different possibilities that I have, which is basically counting from Boolean 0 all the way to Boolean 7, or binary, I should say. And then you can see here that the only time that the expression A B naught C is true is when A is true, B is false, and C is true. And as you can see, the result is 1, or true. So basically, this entire circuit can be reduced to, what is that? It looks like 2 AND gates and an inverter is how this whole thing can be reduced. So to prove it, what I did was I used my circuits software right here. And as you can see here, so I have, let me just go back and forth really fast here. So I have my AB going into an exclusive OR. So there's AB. This is going to be switch A, B, and C. So that's going into an exclusive OR gate. and then I have B and C going into an OR gate. So here's B and C going into an OR gate. And then I have BC going into an exclusive NOR gate, and A as well going into that exclusive NOR gate. So in this software, I don't have an exclusive NOR gate, so I turn an exclusive OR, and then I output that to an inverter. So combined, this is an exclusive NOR gate. And it looks like I have A going into here, and then I have the output of the OR gate going into the exclusive NOR gate. And so that's what you have over here. And then finally, both of these are going to be placed into an AND gate. So here's the AND gate, and then the output from this circuit, and then the output from the exclusive, what are we going to call this, an exclusive NOR gate here. So the output of the exclusive NOR gate goes into here. And what else goes into here? Oh, yes, the exclusive OR gate of A and B. So here's exclusive OR of A and B, and that goes into the second AND gate. And I just simply put an LED over here to show you when it's lit up or not. So in this case, if everything is open, right, so that would be false, false, false. As you can see, the output is false. What we're trying to confirm is this truth table over here, that the only time that the circuit works is when A is on, B is off, and C is on. All right, so only when this is on, off, on will it work. So let me just prove that to you, by the way. So on, off, and then on, it works. Let's see if it's off for everything else. So this is like really the same thing as binary 0. This is binary 1, still off. Binary 2, still off. Binary 3, still off. Binary 4, still off. Now, binary 5, right, that's on, off, on, so that's the option that it works. And then binary 6, off. Binary 7, off. So as you can see over here, for binary 0, 1, 2, 3, 4, 6, and 7, it's off. And only when you have binary, what's this, 1, 2, 4, that's 5, is when the circuit is actually on. So this is how you would use DeMorgan's laws to take a circuit and reduce it, in this case, to something really simple. Save yourself a lot of money. You're saving the circuit a lot of power, and just overall reducing the number of chips that you need to perform this. So this is Professor Robert Solis. I hope this video lesson was helpful. Have a good day. See you next time.